welcome you back. In the last lecture, what we have seen that how to find out the Fourier transform, Fourier cosine transform and Fourier sine transform of a particular function f x, when f x is defined in either minus infinity to infinity or plus infinity to or 0 to infinity, and we have seen the derivation of that one. Let us make a recap of this one first. For Fourier cosine transform, I am just writing FCT. We are just making a recap of this Fourier cosine transform, which I am denoting as capital F c of alpha. This is equals root over 2 by pi 0 to infinity f t into cos of alpha t into dt, so that it will be a function of alpha, and f x equals root over 2 by pi 0 to infinity f c of alpha, capital F c of alpha into cos of alpha x into d alpha. So, Fourier cosine transform of a function x, where the function x is defined in 0 to infinity, is defined as Fourier cosine transform of alpha equals root over 2 by pi 0 to infinity f t cos alpha t dt, whereas f x equals root over 2 by pi 0 to infinity capital F c alpha cos of alpha x into d alpha. So, that the kernel in this case is cos of alpha t is the kernel of this particular transform. So, this is Fourier cosine transform. We are just recapitulating the derivation already we have done in the last lecture. Similarly, Fourier sine transform is being defined as follows, which we will denote afterwards capital F of S of alpha. S means Fourier sine transform, C means Fourier cosine transform. This is equals root over 2 by pi 0 to infinity f t into sine of alpha t dt, and the inverse is f x equals root over 2 by pi 0 to infinity capital F s alpha, capital F s alpha into sine alpha x into d alpha. So, if a function f x is defined in an interval 0 to infinity, Fourier sine transform of f x is defined as capital F s alpha, and this is equals root over 2 by pi 0 to infinity f t into sine alpha t dt, and f x can be derived as root over 2 by pi 0 to infinity capital F s alpha into sine of alpha x into d alpha. So, that if I know the function, I can tell what is the Fourier transform, Fourier sine transform of that function, and also if I know the Fourier sine transform of a function from the second equation, I can tell what is the corresponding f x for which the Fourier sine transform is this one. And the last one is Fourier transform, as I was telling you. Only Fourier transform, in this case the function f x is defined in minus infinity to infinity, and Fourier transform we define as f of alpha equals root over 2 by pi minus infinity to infinity f t into e power minus I alpha t into dt, whereas f x equals root 1 by root over, sorry, this will be not this one, this will be 1 by root over twice pi, 1 by root over twice pi minus infinity to infinity f t into e power minus I alpha t into dt, whereas your f x will be 1 by root over 2 pi minus infinity to infinity capital F of alpha into e power I alpha x into d alpha. This is one, and the second case also you can write down f alpha equals 1 by root over twice pi minus infinity to infinity f t into e power I alpha t into dt, and the f x will be equals to 1 by root over twice pi minus infinity to infinity f alpha into e power minus I alpha t into dt. So, any one of these two can be used over here. So, if a function f x is there which is defined in minus infinity to infinity, the Fourier transform of that function f x can be written as 1 by root over twice pi minus infinity to infinity f t into e power minus I alpha t dt, whereas f x will be 1 by root 2 pi minus infinity to infinity f of alpha into the power I alpha x into dx, and f alpha will be 1 by root 2 pi minus infinity to infinity f t e power I alpha t dt, whereas f x will be equals to 1 by root 2 pi minus infinity to infinity f of alpha e power minus I alpha x. This will be e power minus I alpha x into d alpha. This is not dt, but it will be d alpha. So, therefore, for the first case, if you see, we have taken the kernel as e power minus I alpha t, whereas for the second case we have taken the kernel as e power I alpha t. Any one of these two forms can be used and you will get the correct result for both these. So, please note these three forms for the Fourier transform, Fourier sine transform and Fourier cosine transform, so that if I know the function f x, I can find out the Fourier transform or Fourier cosine transform or Fourier sine transform. And similarly, if I have the knowledge of Fourier transform or Fourier cosine transform or Fourier transform, Fourier sine transform, I can find out what is the corresponding function whose transform is this using this f x or this integral. Now, let us solve certain problems using these transforms. The first one is we want to find out the Fourier sine transform of the function f x equals e to the power minus a x, and hence we want to find the value of the integral 0 to infinity alpha sin alpha x by alpha square plus a square into d alpha. Let us see how we are doing it. So, your function is, suppose f s alpha is the Fourier sine transform of f x of the function f x. So, from the definition of the Fourier sine transform, whatever we have told just now, this is equals to root over 2 by pi, your function f x is equals to e to the power minus a x. So, from the formula you can write down 0 to infinity f x into e to the power sin alpha x dx, because we want to find out the Fourier sine transform. So, it is 0 to infinity f x into sin alpha x dx, your f x is e power minus a x into sin alpha x into dx. So, let us assume that this integral I equals 0 to infinity e power minus a x into sin of alpha x dx, and using integration by parts, this you can write down sin alpha x into e power minus a x by minus a 0 to infinity minus alpha into 0 to infinity cos of alpha x into e power minus a x by minus a into d x. So, this part value I can find out over here. This value at 0 to infinity, this will vanish. Again this part second term we will use the integration by parts, and using integration by parts you will obtain alpha by a into cos of alpha x into e power minus a x by minus a 0 to infinity, plus it will come alpha square by a 0 to infinity sin of alpha x into e power minus a x by minus a into d x. So, if you see this part again will not be there. This part value will be alpha by a. For the first part it will be 1 by a, this is 1, this is 1. So, this is 1 by a minus, this minus is coming, and alpha by a we have taken common. So, alpha by a will come. This integral 0 to infinity e power minus sin alpha e power sin alpha x into e power minus a x dx is nothing but I. This integral has come back, so that I can write down this is nothing but I. So, this value we are getting 1 by a minus alpha by a into this integral is I. We are writing this one. So, that from here you can write down by calculation I equals alpha by alpha square plus a square. So, the value of the integral is alpha by alpha square plus a square, and from here you can tell what is the Fourier sine transform of alpha. So, Fourier sine transform of alpha equals root over 2 by pi will come, and the value of the integral we derived as alpha by alpha square plus a square. So, the first part is over, that is Fourier sine transform of the given function is root over 2 by pi alpha by alpha square plus a square. Next, we have to find out, evaluate the value of this integral 0 to infinity alpha sin alpha x by alpha square plus a square into d alpha. What is the value of this? We have to find out this thing. Now, since we have the Fourier sine transform of this, so using the inverse Fourier sine transform, we can write down f x equals root over 2 by pi 0 to infinity Fourier sine transform of alpha into sine of alpha x d alpha. So, this we are writing from the Fourier inverse Fourier sine transform. Please note this one. At first, we evaluated the value of the Fourier sine transform of the function f x. Now, from the inverse Fourier sine transform, I can write down f x equals root over 2 by pi 0 to infinity f s alpha Fourier sine transform of alpha into sine of alpha x into d alpha, where I know now what is the value of this Fourier sine transform of alpha. So, I can substitute this value here, and I can write down root over 2 by pi 0 to infinity alpha by alpha square plus a square into another root over 2 by pi will come over here. It is there, root over 2 by pi is there, into sine of alpha x into sine of alpha x into d alpha. Therefore, this root over 2 by pi into this will become 2 by pi, and this integral, this one alpha by alpha square plus a square, this I can now write down 0 to infinity alpha into sine alpha x divided by alpha square plus a square into d alpha. So, basically now you see we got back this integral which we have to evaluate 0 to infinity alpha into sine alpha x by alpha square plus a square d alpha. This is equals, here it will be 2 by pi is there, if it goes on that side it will be equals to pi by 2 into f x, and value of f x is nothing but e power minus a x. So, therefore, value of this integral which we are obtaining as pi by 2 into e power minus a x, this is the value of the given integral is this one. So, this is the Fourier sine transform of the function e power minus a x, and from there we are evaluating this integral, that the value of this definite integral is pi by 2 into e power minus a x. So, just let us see over here that this is the problem. So, Fourier's f s is the Fourier sine transform. From the definition we can write down e power minus a x into sine alpha x. So, I am evaluating the integral as we have shown, and ultimately we are obtaining the value of the integral as alpha by alpha square plus a square. Once I obtain this, so I obtain the Fourier sine transform of the function as root over 2 by alpha by alpha square plus s square. Now, we have to evaluate the integral. So, I am using the inverse Fourier sine transform from here. So, that I can write down f x equals root over 2 by pi 0 to infinity f s alpha into sin alpha x d alpha. This now I am substituting the value of Fourier sine transform of alpha, which I derived, and I am evaluating now this 0 to infinity alpha sin alpha x d alpha by alpha square plus s square into d alpha is nothing but pi by 2 into f x, and your f x is e to the power minus a x. So, pi by 2 e power minus a x is the value of the given integral. Now, let us take the same problem. Basically, what I am doing, I have taken the same function e power minus a x, but now we want to find out the Fourier cosine transform of this function e power minus a x, and from here we want to evaluate the value of the integral 0 to infinity cos of alpha x by alpha square plus s square into d alpha. Let us see this one. Your f x is e power minus x, and we want to find out the Fourier cosine transform, which I am writing as f c alpha is the Fourier cosine transform of f x. So, from the formula we can write down root over 2 by pi 0 to infinity e power minus a x into cos of alpha x into d x. So, please note that your function is e power minus a x. The formula is f x into cos of alpha x d x. Again, like previous problem, I am just assuming I equals 0 to infinity e power minus a x into cos of alpha x d x. Using integration by parts, I can evaluate this integral cos of alpha x into e power minus a x by minus a, 0 to infinity it will come, plus alpha into 0 to infinity sin of alpha x into e power minus a x by minus a into d x. So, here I will obtain the value as 1 by a in one case for 0, and here it will be minus for the second term. For the first term I am getting the value as 1 by a. For the second term again I will use the integration by parts. So, that I will obtain minus alpha by a into sin of alpha x into e power minus a x by minus a 0 to infinity plus alpha square by a 0 to infinity cos of alpha x into e power minus a x by minus a into d x. And this integral 0 to infinity cos of alpha x into e power minus a x dx, this is nothing but the integral I. So, that this equals, I can write down 1 by a minus this value you will obtain as this part will vanish, second term will vanish in the last one. So, this will be alpha square by a square into I. So, I am getting I equals 1 by a minus alpha square by a square into I, and from here you can find out I will be equals to a by alpha square plus a square. So, this I am obtaining from here I equals to a by alpha square plus a square. So, once I have obtained the value of this integral, now I can write down what is my Fourier cosine transform of the function. So, Fourier cosine transform of alpha is equals to root over 2 by pi a by alpha square plus a square. So, once I have obtained the Fourier cosine transform, now we have to evaluate the integral. Again we will follow the same process, that is using inverse Fourier cosine transform. I can write down what will be the value of f x. Your f x will be root over 2 by pi 0 to infinity Fourier cosine transform of alpha into cos alpha x into d alpha. So, that it will be a function of alpha. Substitute the value of Fourier cosine transform of alpha, whatever we obtain. So, root over 2 by pi is there, it becomes 2 by pi 0 to infinity a by alpha square plus a square into cos of alpha x into d alpha. So, from here the value of the integral 0 to infinity a by alpha square plus a square into cos of alpha x d alpha, this is equals to pi by 2 a will come, pi by a will come outside. So, pi by 2 a into f x, and your f x is nothing but e power minus a x. So, that the value of the given integral will be the pi by 2 into e power minus a x. So, like this way we can find out the Fourier sine transform, Fourier cosine transform of any function. Let us see quickly over here. We are getting the value of this, f c is this one, and from here Fourier cosine transform of alpha using the definition, we can write down the root over 2 by pi 0 to infinity e power minus a x into cos of alpha x into d x. Now, we evaluate the integral using integration by parts, and ultimately I obtain the value of the integral I as a by alpha square plus a square. So, we obtain the Fourier cosine transform of the function f x as root over 2 by pi into a by alpha square plus a square. Once I obtain this, I can write down f x equals this using inverse Fourier cosine transform, and I can write down f x equals root over 2 by pi 0 to infinity f c of alpha cos alpha x d alpha, where f c of alpha is known to me. If I substitute the value, then I can write down the value of the integral as 0 to infinity cos of alpha x alpha square plus a square d alpha is nothing but pi by 2 a into f x, where f x is e power minus a x. Now, let us take another problem. Find the Fourier cosine transform of the function f x equals 1 when it lies between 0 to a and 0 for x greater than equals a, and hence we have to evaluate the value of the function, value of the integral 0 to infinity sine of a alpha cos of alpha x by alpha d alpha. So, for this one we have to, since we have to find out the Fourier cosine transform. So, Fourier cosine transform of alpha is nothing but root over 2 by pi 0 to infinity f x into cos of alpha x into d x. And if I evaluate the integral, because I have to evaluate it from 0 to 1 only, the value is a, it is a simple integral. So, we are writing the directly the value as sine of a alpha by alpha. So, Fourier cosine transform of this basically only you will taking the limit from 0 to a only, function has been defined over here, and evaluating the simple integral, I will obtain the value as sine a alpha by alpha. So, that Fourier cosine transform of the given function is sine a alpha by alpha. Now, your f x using inverse Fourier transform, we can write down f x equals root over 2 by pi into 2 by pi. So, this will be 2 by pi 0 to infinity. Your function is Fourier cosine transform, that is Fourier cosine transform value is sine a alpha by alpha. Directly I am putting into cos of alpha x d alpha. So, that you can write down 0 to infinity sine of a alpha cos of alpha x by alpha into d alpha. This is equals to pi by 2 into f x. Again f x we know it, in 0 to a it is pi by 2. So, the value in 0 to a value of f x is 1. So, it will be pi by 2 only in 0 to a and 0 whenever x is greater than equals a. So, that the value of this given integral becomes pi by 2 when x lies between 0 to a and 0 whenever x is greater than equals a. And if I see this thing, just quickly you can go through this, and Fourier cosine transform I am writing. From here I am writing the inverse Fourier transform, that is f x, and directly I can tell what is the value of the given integral. Now, let us take the another problem. We want to find out the Fourier sine transform of the earlier function, and we want to evaluate the integral. So, please note one thing, not only we are evaluating the Fourier sine transform, Fourier cosine transform of any function, but also simultaneously using this Fourier cosine or Fourier sine transform, I can evaluate the value of some integral, which may become difficult for me to evaluate using the normal integration processes. So, therefore, it has double advantages. I am not only finding the Fourier transform or Fourier sine or Fourier cosine transforms, but also I am trying to find out the value of some integral also, which may become difficult for us to evaluate the integral using the integration properties. Let us see the solution of this one. Your Fourier sine transform is equals to of alpha. This is equals to basically root over 2 by pi 0 to infinity your f t into sine of alpha t into dt. This is basically you are writing as root over 2 by pi into 0 to a. The value of the function is 1. So, sine of alpha t dt. If you evaluate the value of this, you will obtain this value as root over 2 by pi into 1 minus cos of alpha a alpha divided by alpha will come. So, the Fourier sine transform of the function is root over 2 by pi 1 minus cos of a alpha by alpha, and from here using inverse Fourier sine transform, I can write down f x equals 2 by pi 0 to infinity 1 minus cos of a alpha by alpha into sine of alpha x d alpha. So, that the value of the given integral 0 to infinity 1 minus cos of a alpha into sine of alpha x by alpha d alpha. This is equals to pi by 2 will go there. So, it will be pi by 2 into f x, and again we know f x is 1 for 0 to a. So, it will be pi by 2 whenever x lies between 0 to a, and for x greater than equals a, this will be equals to the 0 for this case. So, I hope you have understood the how to find out the Fourier cosine transform or sine transform of the function. Just let us see this problem first, and once the problem is this. So, Fourier sine transform I am writing in this way. From here you are writing f x equals 2 by pi 0 to infinity 1 minus cos of a alpha 1 minus cos of a alpha by alpha into sine alpha x d alpha, and value of the integral which I want to find out is becoming pi by 2 into f x. So, that it is pi by 2 whenever 0 less than x less than a, and pi for x greater than equals a, the value of the definite integral is equals to 0. So, two things we have done in this lecture. One is how to find out the Fourier cosine transform or Fourier sine transform of a function whenever the function is given to me, and also whenever I am finding the Fourier transform, Fourier sine or Fourier cosine transform of the function, from using that inverse Fourier cosine or inverse Fourier sine transform, I can find out the value of some other integral also. This is the advantages of using this Fourier sine and Fourier cosine transform.